In the last video, we talked about continuous functions, and in this video, we're going to talk about a special type of continuous functions called uniformly continuous functions. So we're going to step back and look at when we were proving functions were continuous and figure out which unknowns we were treating as constants and which we were treating as variables. We're going to make some adjustments to those assignments to define uniform continuity, and then we're going to work an example. So when we were proving that the function f is continuous at, say, x equals a, we want to ask the question, what real number quantities were we considering to be constants and which we were considering to be variables? So continuous at x equals a, what the official definition is for all epsilon greater than 0, there exists delta greater than 0, such that whenever x is a real number with absolute value of x minus a less than delta, then absolute value of f of x minus f of a is less than epsilon. And there are a lot of variables in there. We see, or unknowns I should say, epsilon, delta, x, f of x, a. And some of those we treated as constants and some of them we didn't. The ones we treated as constants were epsilon, delta, and a. Once we got an epsilon, that epsilon stayed the same throughout the entire computation that we did in proving that it was continuous. Same with delta. Delta could be based on epsilon, could be based on a. Those are both constants. And a is, of course, the point that we're finding the function continuous at, so that was the same throughout the entire computation as well. And if we looked at x and f of x, those could definitely vary, right? X could vary. It could be any number that makes absolute value of x minus a less than delta, and that's a ton of numbers. And then, of course, f of x varies as well because x varies. So our model for being uniformly continuous is going to be let f be a function from an interval I to r. We call f uniformly continuous on I if we can prove that f is continuous by treating the point a in I as a variable. So, and of course we also treat x as a variable. We're not going to make any changes to that one. So the only unknowns we treat as constants are going to be epsilon and delta. And to look at why this is significant, let's think back to when we were proving that f of x equals x squared was continuous at a point x equals a, and we're just looking at x being a positive real number. So when we proved this, we wanted to make absolute value of x squared minus a squared less than epsilon. When we solved for absolute value of x minus a, we got that was less than epsilon over x plus a. We knew that epsilon over x plus a was an inappropriate delta because x was a variable, right? X could change, but we needed things that were constant. So we went through a lot of work to say, okay, first we're going to have delta be no bigger than a, right? And so we solved our inequalities and got that x plus a was between a and 2a. And that helped us come up with a delta that was the minimum of a and epsilon over a. And those were appropriate possibilities for delta because a was a constant. Right? So we can't use that proof to show that f is uniformly continuous though, because in uniform continuity, a cannot be a constant. And in fact, spoiler alert, that function is not going to be uniformly continuous, no matter how clever we are. So our formal definition is let I be an interval and let f be a function from I to r. We say that f is uniformly continuous on I if for every epsilon greater than 0, there exists a delta greater than 0 such that for all x and a in the interval I, absolute value of x minus a is less than delta, then absolute value of f of x minus f of a is going to be less than epsilon. So ordinary continuity, the function is continuous at a single number in the domain, a single a. But notice that this one, for uniform continuity, the function is uniformly continuous on an entire interval. That is why a must be considered a variable, because it could be any number in the interval that makes up the domain. So here's a theorem of a function that is uniformly continuous, and we can actually prove it. Let f be a linear function, so f of x is mx plus b. Then f is uniformly continuous on all the real numbers. So that's a pretty big interval, right? So here's our strategy. Guess what? It's the same strategy that we always had. We want the absolute value of f of x minus f of a less than epsilon, and we want to see what that tells us about the absolute value of x minus a. So we plug in our values for f of x and f of a. We notice that the b's cancel, and we can factor out an absolute value of m. So we end up with absolute value of f of x minus a equal to absolute value of m times absolute value of x minus a. We want that to be less than epsilon. We divide both sides by absolute value of m to get absolute value of x minus a is less than epsilon over absolute value of m. We can now let delta equal epsilon over absolute value of m because both epsilon and absolute value of m are being considered constants here. We don't have a as part of our delta, so that will be a constant. And then we do the rest of the proof the same as regular continuity, and that will prove that f is uniformly continuous over all the real numbers. So for our proof of uniform continuity, not much different than proving a function is continuous. The only significant difference is we have to work harder to find an appropriate delta. We have to make sure it does not depend on any of the points, any of the input values from the function. But other than that, the proof is exactly the same as ordinary continuity. So I think you're ready to work on the activities for uniform continuity. Just go ahead and click on the link below this video.